All right, everyone, welcome. I'm genuinely excited to dive into one of the most important, yet often misunderstood technologies in our digital lives today, OAuth 2.0. You know that magical moment when you click Log in with Google on a new app and suddenly you're in? Or when your fitness app somehow gets data from your smartwatch without you entering a password? That's OAuth 2.0 working behind the scenes, and today we're pulling back the curtain. Whether you're a developer building the next killer app, a security professional protecting systems, or just someone who's curious about how all this digital stuff actually works, you're in the right place. We're going to start from zero and build up to some pretty advanced concepts, but I promise to keep it interesting and relatable. By the end of our time together, you'll not only understand what OAuth 2.0 is, but you'll also know why it matters and how to use it without shooting yourself in the foot security-wise. Let me ask you something. Have you ever stopped to think about what's really happening when you connect a new app to your Facebook or Google account? Or how that photo printing service gets access to your Google Photos without you handing over your password? That's what we call the delegation dilemma. Figuring out how to let one service access your data in another service without turning it into a security nightmare. Before OAuth 2.0 came along, we had this scary thing called the password anti-pattern. Picture this. You find this awesome photo printing service, and it says, hey, just give us your Google username and password, and we'll grab your photos and print them for you. Would you feel comfortable doing that? I hope not. This approach was basically a security disaster waiting to happen. These third-party services would store your password, often in plain text. Yikes, making them incredibly attractive targets for hackers. Plus, you were giving them the keys to your entire Google kingdom, not just access to your photos. And if you wanted to revoke access later, you'd have to change your Google password, which would then break access for every other service you use. OAuth 2.0 was created specifically to solve this fundamental problem. And here's something that trips up a lot of people. It's not actually an authentication protocol. Instead, it's an authorization framework that lets you grant limited access to your data without ever sharing your credentials. Think of it like giving a valet key to your car. It lets someone park your car, but doesn't give them access to your glove compartment or trunk. You're giving them limited permission for a specific purpose. Since its publication in 2012, OAuth 2.0 has become the industry standard for delegated authorization. It's the invisible technology powering all those seamless integrations we use every day. So why should you care? Well, if you're building applications that need to access user data from other services, or if you're responsible for securing such systems, understanding OAuth 2.0 isn't just helpful, it's absolutely essential. OAuth 2.0 didn't just appear out of thin air. It actually had a predecessor called OAuth 1.0. Now, OAuth 1.0 worked, but it was notoriously complex to implement. Imagine having to generate these complex cryptographic signatures for every single API request. That's what developers had to deal with. It was error-prone and created significant barriers to adoption. The designers of OAuth 2.0 looked at this experience and said, there's got to be a better way. So they made a fundamental architectural shift. Instead of requiring complex client-side cryptography, they decided to offload the responsibility of securing communication to the transport layer, specifically Transport Layer Security, or TLS, which is the technology that powers HTTPS. This was such a smart design choice and reflects a broader trend in web protocol development, prioritizing developer experience and ease of implementation to drive widespread, correct adoption. By making the secure path the easier path, the protocol designers recognized that a slightly less theoretically complex but much more implementable standard would actually lead to better real-world security. What happens if we don't make security easy to implement? Well, we've all seen this movie before. Developers either skip security features altogether or implement them incorrectly, creating vulnerabilities. The OAuth 2.0 designers learned from this and made the secure approach the straightforward one. This simplification was absolutely crucial to OAuth 2.0's rapid adoption by major technology companies like Google, Microsoft, and Facebook. Today, it's the foundation of modern API security, enabling all those interconnected digital experiences we've come to expect and rely on. Now that we understand how OAuth 2.0 came to be, let's meet the key players in this ecosystem. To really understand how this works, we need to get familiar with the key players in this ecosystem. The framework defines 4 primary roles that interact during any authorization flow. First up, we have the resource owner. This is typically you, the end user who owns the data and is authorizing an application to access it. In our analogy, if you have a safe with valuable items, you're the owner of that safe. Next is the client. This is the application that's requesting access to the protected resources on your behalf. The term client is intentionally broad. It could be a server-side web application, a mobile app, or even a browser-based single-cage application. In our analogy, the client is like a trusted friend asking to borrow a specific item from your safe. Now, clients fall into 2 categories based on their ability to keep secrets: confidential clients and public clients. Confidential clients, like traditional server-side web applications, can securely store their credentials. Public clients, like SPAs or mobile apps, can't keep secrets because their code is exposed to users or can be decompiled. Then we have the authorization server. This is the gatekeeper that authenticates you, the resource owner, and obtains your consent. It's the component you directly interact with to approve or deny an access request. In our analogy, this is like the bank's security guard who verifies your identity and permission slip before issuing a key to your friend. Finally, there's the resource server. This hosts the protected resources, typically an API that the client wants to access, like the Google Calendar API or Twitter API. The resource server validates access tokens to determine if requests should be served. In our analogy, this is the vault where your safe is located. Why is understanding these roles so important? Because they form the foundation of every OAuth 2.0 flow. The distinction between public and confidential clients is particularly important, as it's driven the evolution of OAuth 2.0's security mechanisms, including the development of extensions like PKCE, which we'll explore later. Now that we know the players, let's look at the tools they use to interact with each other. These are essentially the building blocks of OAuth 2.0. The access token is the primary credential used by clients to access protected resources. It's a string representing specific permissions for a defined duration. Access tokens are bearer tokens, meaning whoever possesses the token can use it, so they must be protected. In modern implementations, they're often formatted as JSON Web Tokens, or JWTs, which can carry data about the authorization. The refresh token is an optional, long-lived credential that clients can use to obtain new access tokens when the current ones expire. This lets you maintain authorized access without repeatedly entering your credentials. Refresh tokens are extremely sensitive and must be stored securely. They're only ever sent to the authorization server, never to the resource server. The authorization code is a temporary single-use code that the authorization server issues to the client via your browser. The client then exchanges this code in a secure, back-channel communication with the authorization server to get an access token and optionally a refresh token. This code acts as an intermediary, preventing the more powerful access token from being exposed in the less secure browser environment. Scopes are a crucial mechanism for implementing the principle of least privilege. They're strings that define specific permissions the client is requesting, like read photos or write calendar. When you're prompted for consent, these scopes are displayed, letting you make an informed decision about what access you're granting. Finally, we have client ID and client secret. These are the credentials used to identify and authenticate the client with the authorization server. The client ID is public, while the client secret is confidential and must be kept secure. It's used by confidential clients to authenticate themselves when exchanging an authorization code for an access token. These artifacts work together to create a secure, flexible authorization framework that can adapt to various use cases while maintaining security. Think of them as different tools in a toolbox, each with a specific purpose, but all working together to build a secure system. Now let's see how these tools are used in the OAuth 2.0 flow. Let's walk through the abstract OAuth 2.0 flow, which consists of 6 main steps. This generic model illustrates the fundamental sequence of interactions that underpins most OAuth 2.0 flows. First, the client initiates the flow by requesting authorization from you, the resource owner. This typically happens indirectly by redirecting your browser to the authorization server. Second, if you grant the request, the client receives an authorization grant. This grant is a credential representing your authorization. The specific form of this grant depends on the authorization grant type being used. It could be an authorization code or even an access token itself. Third, the client requests an access token from the authorization server by presenting the authorization grant it just received. In this step, the client must also authenticate itself with the authorization server using its client ID and client secret. Fourth, the authorization server authenticates the client and validates the authorization grant. If both are valid, it issues an access token and, optionally, a refresh token to the client. Fifth, the client uses the access token to make requests to the resource server to access the protected resource. The access token is typically included in the authorization header of the HTTP request. Finally, the resource server validates the access token. If the token is valid and has the necessary scope for the requested operation, the resource server processes the request and returns the protected resource to the client. This abstract flow reveals a deliberate and critical security design: the separation of the front channel from the back channel. The front channel refers to interactions that happen via your browser, where data can be exposed in URLs, browser history, or to client-side scripts. In contrast, the back channel refers to direct server-to-server communication over a secure TLS connection. The most sensitive credentials, like the client secret and the final access token, are transmitted exclusively on the back channel, shielding them from exposure in your browser. This architectural separation is a cornerstone of OAuth 2.0's security model. Why is this separation so important? Well, imagine the difference between shouting a secret across a crowded room versus whispering it in a private soundproof booth. The front channel is like that crowded room, potentially exposed to eavesdroppers, while the back channel is like the private booth, secure and confidential. Let's dive deeper into this critical security design. This separation of front channel and back channel is so important that it deserves its own slide. This architectural choice is fundamental to OAuth 2.0's security model. The front channel is the less secure path. It's what happens in your browser. Data here can be exposed in URLs, browser history, or to client-side scripts. It's like having a conversation in a crowded room. You know others might overhear, so you only share non-sensitive information. In OAuth 2.0, the front channel is used for steps that involve browser redirects, like the initial authorization request and the delivery of the authorization code. These are temporary, single-use credentials that have limited power if intercepted. The back channel, on the other hand, is the secure path: direct server-to-server communication over TLS. It's like having a private, encrypted conversation in a soundproof room. This is where sensitive information is transmitted. In OAuth 2.0, the back channel is used for exchanging the authorization code for the powerful access token. This ensures that the access token is never exposed in the browser environment, significantly reducing the risk of token theft. Flows that violate this principle by returning the access token directly in the front channel, like the now deprecated implicit grant, are considered insecure, precisely because they expose the bearer token to the risks of the browser environment. Think about it this way. Would you rather hand someone a key to your house in a crowded public square or in a private, secure room? The back channel is that private, secure room where the most sensitive exchanges happen. This separation is a powerful security pattern that's worth understanding deeply, as it applies to many security protocols beyond just OAuth 2.0. It's all about keeping sensitive information away from potentially compromised environments. Now that we understand this fundamental security principle, let's look at the different ways OAuth 2.0 can be implemented through various grant types. OAuth 2.0 defines several grant types, which are distinct flows for obtaining an access token. The choice of which grant type to use is critical and depends almost entirely on the type of client application you're developing and its security context. It's important to understand that the portfolio of grant types isn't a menu of equal choices. Instead, it's more like an evolutionary record of the framework adapting to diverse and changing application architectures, each with unique constraints. The most important question to ask when choosing a grant type is, can my client application securely store a secret? If the answer is yes, typically for server-side web applications running in a controlled environment, then the authorization code grant is your best choice. If the answer is no, which is the case for single-page applications running in browsers or native mobile apps whose code can be inspected or decompiled, then the authorization code grant with PKCE is the recommended approach. For non-interactive machine-to-machine scenarios where there's no user involved, like background services or microservices calling each other, the client credentials grant is the appropriate choice. The implicit grant and resource owner password credentials grant are considered legacy flows that should be avoided in new applications due to significant security vulnerabilities. There are also specialized flows, like the device authorization grant for input-constrained devices like smart TVs, and the refresh token grant for renewing access without user interaction. Choosing the right grant type is one of the most important security decisions you'll make when implementing OAuth 2.0. What happens if you choose the wrong one? You could end up with significant security vulnerabilities in your application. Let's take a closer look at the most secure and widely used grant type, the authorization code grant. The authorization code grant is the primary and most secure flow in OAuth 2.0. It's intended for confidential clients, typically traditional server-side web applications that can securely store a client secret. Let's walk through how it works. First, the client application redirects your browser to the authorization server's authorization endpoint. This request includes several parameters: response type equals code to specify the grant type, the application's client ID, a pre-registered redirect URI where you'll be sent back, the requested scope of permissions, and a state parameter. The state parameter is a random, opaque value generated by the client to maintain state between the request and callback, and to mitigate cross-site request forgery attacks. Next, you authenticate with the authorization server, perhaps by logging in, and are presented with a consent screen detailing the permissions the client is requesting. If you grant consent, the authorization server redirects your browser back to the client's specified redirect URI. This redirect includes the single-use authorization code and the original state value in the query string. The client application receives this request at its redirect URI. It first validates that the received state value matches the one it originally sent, ensuring the request is legitimate and not a CSRF attack. Then, the client makes a secure back-channel post request from its server to the authorization server's token endpoint. This request includes the authorization code, the redirect URI, and its own authentication credentials, client ID, and client secret. Finally, the authorization server verifies the code, the redirect URI, and the client's credentials. If everything checks out, it responds with a JSON object containing the access token and, optionally, a refresh token. The security of this flow lies in the separation of channels we discussed earlier. The powerful access token is delivered directly to the client's backend over the secure back channel and is never exposed in your browser, minimizing the risk of leakage. This makes the authorization code grant the gold standard for server-side applications. But what if your application can't securely store a secret? Let's look at how OAuth 2.0 addresses that challenge. But what if your client application can't securely store a secret? This is the case for single-page applications running in browsers or native mobile apps. The standard authorization code flow has a vulnerability here because a public client can't authenticate its request to the token endpoint. This opens the door to an authorization code interception attack. Imagine a malicious application on your device intercepting the authorization code as it's delivered back to the legitimate app. This malicious app could then exchange the code for an access token and gain unauthorized access to your resources. This is where PKCE comes in. PKCE, pronounced PKCE, stands for Proof Key for Code Exchange. It's defined in RFC 7636 and extends the authorization code flow with additional steps to mitigate this attack. Here's how it works. Before the flow begins, the client application generates a cryptographically random string called the code verifier. It then creates a code challenge by hashing the code verifier, typically using SHA-256 and base64 URL encoding the result. During the authorization request, the client includes two additional parameters, the code challenge and the code challenge method, like S256. The authorization server stores the challenge and associates it with the authorization code it generates. Later, during the token exchange, the client includes the original unhashed code verifier in its request to the token endpoint. The authorization server receives this code verifier, applies the same hashing algorithm specified by the code challenge method, and compares it to the code challenge it stored earlier. If they match, it proves that the client making the token request is the same one that initiated the authorization flow. Only then does it issue the access token. PKCE effectively creates a dynamic, one-time secret for each authorization request. Even if a malicious app intercepts the authorization code, it can't exchange it for a token because it doesn't possess the secret code verifier. This makes the authorization code flow secure for public clients, which is why it's now considered the industry best practice for SPAs and mobile apps. What would happen if we didn't have PKCE? Public clients would be forced to use less secure flows, creating significant security risks in modern application architectures. Not all OAuth flows involve a user granting permission to an application. Sometimes we need non-interactive, machine-to-machine authorization, where the client is acting on its own behalf, not on behalf of a user. This is where the client credentials grant shines. Imagine you have a background service that needs to access an API, or microservices calling each other, or a command line tool performing automated tasks. These scenarios don't involve a user granting consent in real time. They're purely machine-to-machine interactions. The client credentials grant is the simplest of all the flows. The client makes a single POST request directly to the authorization server's token endpoint. The request body contains grant type equals client credentials and the client's credentials, typically client ID and client secret. The authorization server authenticates the client and, if successful, immediately returns an access token. There's no user interaction, no consent screen, and no browser redirection. In this flow, permissions aren't delegated by a user. Instead, they're granted directly to the application itself by an administrator of the service. These are often referred to as application permissions or roles, which define what the service is allowed to do on its own. For example, a data processing service might be granted permission to read from a specific database and write to another without any user involvement. Or a monitoring service might be granted permission to read system metrics across multiple services. The Client Credentials Grant is perfect for backend services, daemons, and other non-interactive scenarios where user involvement isn't feasible or necessary. It's straightforward, secure, and efficient for machine-to-machine communication. Why is this flow important in modern architectures? With the rise of microservices, serverless computing, and automated systems, the need for secure machine-to-machine communication has never been greater. The Client Credentials Grant provides a standardized, secure way to handle these scenarios. While these are the primary flows you'll encounter, there are some legacy and specialized flows you should be aware of as well. While modern applications should gravitate toward the authorization code with PKCE flow, it's important to understand legacy flows that you might still encounter. The implicit grant was originally designed for SPAs. However, due to significant security vulnerabilities, it's now considered a legacy flow and is officially deprecated. The mechanics are simple. The client requests response type equals token, and after user consent, the authorization server returns the access token directly in the URL fragment of the redirect URI. This flow is highly insecure because it exposes the access token directly in the browser. The token can be leaked through browser history, web server logs, or referrer headers. It also doesn't support the issuance of refresh tokens, leading to poor user experience, as users must re-authenticate frequently. If you encounter applications still using this flow, they should be migrated to the authorization code with PKCE flow as soon as possible. The Resource Owner Password Credentials Grant, or ROPC, should be used only as a last resort in scenarios where redirect-based flows are impossible and there's a very high degree of trust between the user and the client. This typically applies only to legacy applications or first-party clients, like a desktop application provided by the service itself. In this flow, the client application directly collects your username and password and sends them in a post request to the token endpoint with grant type equals password to obtain an access token. This fundamentally breaks the core principle of delegated authorization by forcing the client to handle your primary credentials. It increases the attack surface and should be avoided whenever a redirect-based flow is feasible. Understanding these legacy flows is important, not so you can implement them, but so you can recognize them in existing systems and understand why they should be replaced with more secure alternatives. What happens if you encounter these flows in existing systems? It's important to prioritize migrating them to more secure alternatives as they represent significant security risks. Beyond these legacy flows, there are also specialized flows designed for specific use cases. Beyond the main grant types, OAuth 2.0 includes specialized flows for unique use cases. The device authorization flow is designed for input-constrained devices that lack a browser or an easy way to enter text, like smart TVs, IoT devices, or digital picture frames. Think about trying to log in to Netflix on your smart TV. Typing a complex password with a remote control would be frustrating. The process is clever. The device makes a request to the authorization server and receives a user code and a verification URI. It displays these to you, and you then use a secondary device, like your smartphone or laptop, to navigate to the URI, log in, and enter the code to approve the request. Meanwhile, the input-constrained device polls the authorization server until it receives an access token. This flow decouples authentication from the device itself, making it possible for devices with limited input capabilities to securely access protected resources. The refresh token grant isn't a primary authorization flow, but a mechanism for renewing access. When an access token expires, which they do frequently for security reasons, a client holding a refresh token can make a post request to the token endpoint with grant type equals refresh token and the refresh token. The authorization server then issues a new valid access token, allowing for long-lived sessions without requiring you to log in again. Refresh tokens are powerful and long-lived, so they must be stored securely. Best practices include implementing refresh token rotation, where a new refresh token is issued each time one is used, to detect and invalidate stolen refresh tokens. These specialized flows demonstrate the flexibility of OAuth 2.0, showing how it can be adapted to diverse use cases while maintaining security principles. Now that we've covered the various flows, let's see how they come together in a real-world example. To make these abstract concepts concrete, let's walk through a common end-to-end example. A user signing up for a new third-party web application called To-Do app using their existing Google account. This scenario uses the modern and secure authorization code with PKCE flow, as To-Do app is a single-page application. First, you navigate to todoapp.com and click the Sign In with Google button. This triggers the OAuth 2.0 flow. Before redirecting you, the To-Do app's client-side JavaScript code generates a random code verifier and computes the corresponding code challenge by hashing it and then base64 URL encoding the result. To-Do app then constructs an authorization URL and redirects your browser to Google's authorization endpoint. This URL contains several critical parameters, including the response type equals code, To-Do app's client ID, a redirect URI, the requested scope like OpenID email profile for identity information, a random state parameter for CSRF protection, and the PKCE parameters. Now you're on a Google-hosted page. If you're not already logged into your Google account, you'll be prompted to do so. After successful authentication, Google displays a consent screen that clearly states what To-Do app is requesting. To-Do app wants to view your name, email address, language, and profile picture. You review the permissions and click Allow. Google's authorization server then redirects your browser back to To-Do app's specified redirect URL with the authorization code and the original state value appended to the URL. The client-side code at To-Do app immediately parses the URL to extract the authorization code and state. It first verifies that the received state matches the one it generated earlier to ensure the request is legitimate. Then, the client-side code sends the authorization code to To-Do app's own backend server. This is a crucial step to move the process from the insecure browser environment to the secure server environment. To-Do app's backend server now makes a secure server-to-server post request to Google's token endpoint, including the authorization code, its client credentials, the redirect URI, and the original unhashed code verifier. Google's token endpoint validates all this information. Critically, it hashes the provided code verifier and confirms that it matches the code challenge from the initial authorization request. If all checks pass, it returns a JSON payload to To-Do app's backend containing an access token, a refresh token, and an ID token. Finally, To-Do app's backend can use the access token to make authenticated API calls to Google's user info endpoint to retrieve your profile information. It can also validate the ID token to confirm your identity and use the information within it to create a new account or log you into an existing one in its own database, establishing its own session for you. This flow demonstrates how OAuth 2.0 enables secure, seamless authentication and authorization across different services while protecting your credentials and giving you control over what data you share. So, why has OAuth 2.0 become so widely adopted? Let's look at its key advantages. OAuth 2.0 has become the cornerstone of modern API security for good reason. Its design offers significant benefits that have driven its widespread adoption. First and foremost is enhanced security. By eliminating the password anti-pattern, OAuth 2.0 drastically reduces the risk and impact of credential compromise. If an access token is stolen, it provides only limited access for a short period and can be revoked without affecting your primary password. This is a massive improvement over the old model, where a compromised password meant full access to your account. Second, OAuth 2.0 significantly improves user experience. For end users, it enables seamless and convenient login and integration experiences. Features like Login with Google reduce sign-up friction and password fatigue, which can lead to higher user adoption rates and satisfaction. Think about how many apps you've signed up for using your Google or Facebook account. It's much easier than creating yet another username and password. Third, OAuth 2.0 provides granular user control and privacy. The use of scopes empowers you by giving you explicit control over what data you share with third-party applications. You can grant only the necessary permissions and, crucially, can revoke an application's access at any time through your account settings on the service provider's site. This enhances both privacy and user trust. Finally, OAuth 2.0 offers standardization and flexibility. As a widely adopted industry standard, it fosters interoperability between services and provides a rich ecosystem of well-vetted libraries and tools for developers. Its variety of grant types makes it a flexible framework capable of securing a wide range of application architectures, from traditional web servers to mobile apps and IoT devices. These advantages have made OAuth 2.0 the de facto standard for API authorization, enabling the interconnected digital experiences we've come to expect while maintaining security and user control. But while OAuth 2.0 offers many benefits, it's not without its challenges. Let's look at some important security considerations. While OAuth 2.0 offers significant advantages, its flexibility also introduces complexities and potential security pitfalls that must be carefully managed. One major challenge is implementation complexity. The OAuth 2.0 framework leaves certain aspects open to interpretation, and the existence of multiple grant types can be confusing for developers. Choosing the wrong flow for a given application type or implementing a flow incorrectly is a primary source of security vulnerabilities. To mitigate this, adhere strictly to current best practices, which mandate using the Authorization Code Grant with PKCE for all public clients. Utilize mature, well-maintained libraries provided by the Identity Service or the open-source community, rather than implementing the flows from scratch. A deep understanding of the security model of the chosen grant is paramount. Another significant risk is token hijacking and leakage. Access tokens are bearer tokens, meaning possession equals access. They're valuable targets for attackers and can be stolen in various ways, including through cross-site scripting attacks that exfiltrate the token from client-side storage or via insecure redirect URIs. To mitigate this risk, implement a robust token management strategy. Use short-lived access tokens, typically 5 to 15 minutes, and long-lived refresh tokens. Implement refresh token rotation, where a new refresh token is issued each time one is used to detect and invalidate stolen refresh tokens. Store tokens in the most secure location available for the client type. Secure HTTP-only cookies for web apps or the platform's keychain for mobile apps. A common and critical vulnerability occurs when an authorization server performs weak validation of the redirect URI parameter. If it only matches the domain, an attacker could register a redirect URI like http://example.com/attacker.net, or use an open redirect on the legitimate domain to have the authorization code or token sent to a malicious site. To prevent this, the client must register the most specific and complete redirect URI possible with the authorization server. The authorization server, in turn, must enforce an exact string match against the registered URIs. Wildcard matching should be strictly forbidden. Finally, the use of OAuth 2.0 creates a dependency on third-party identity providers. If a provider like Google or Microsoft experiences an outage, it can prevent users from logging into any application that relies on it. In an enterprise context, the ease of use can lead to shadow IT, where employees authorize numerous unsanctioned third-party OAuth applications to access corporate data, creating significant data leakage and compliance risks. To mitigate these risks, consider supporting multiple identity providers or a direct credential-based login as a fallback for mission-critical applications. For enterprises, it's essential to use cloud access security broker tools or similar platforms to monitor, audit, and control which third-party OAuth applications employees are permitted to authorize. Understanding these risks and implementing appropriate mitigations is crucial for maintaining the security benefits that OAuth 2.0 promises. Now, let's see how OAuth 2.0 fits into the broader identity and access management landscape. OAuth 2.0 doesn't operate in a vacuum. It's part of a broader ecosystem of identity and access management protocols. Understanding its relationship with two other major standards, Security Assertion Markup Language, or SAML 2.0, and OpenID Connect, or OIDC, is crucial for anyone working in this space. The primary point of confusion arises because all three can be used to implement Single Sign-On, or SSO, but they solve fundamentally different problems. OAuth 2.0, as we've established, is an authorization framework. Its core question is, what is this application allowed to do on my behalf? It's designed for delegated access control, particularly for APIs. It's a modern, lightweight protocol that typically uses JSON for its data structures and communicates over standard HTTP-based APIs. Its sweet spot is securing API access between applications, enabling social media integrations, and powering connect my account to, etc. scenarios. OpenID Connect, or OIDC, is a simple authentication layer built directly on top of OAuth 2.0. Its core question is, who is this user? It provides a standard way to verify a user's identity. OIDC is not a separate protocol, but an extension of OAuth 2.0. A client initiates a standard OAuth 2.0 flow, but includes a special scope value, OpenID. When the authorization server, now called an OpenID provider, sees this scope, it knows the client is performing an OIDC authentication request. In addition to the standard access token, the provider issues a special credential called an ID token. The ID token is a signed JWT that contains verifiable claims about the authenticated user, such as their unique identifier, name, email, and when they authenticated. OIDC is the modern standard for implementing SSO for consumer-facing web and mobile applications, powering virtually all login with Google, login with Facebook, etc. buttons. SAML 2.0, on the other hand, is an older, more heavyweight open standard for exchanging authentication and authorization data between parties, known as an identity provider and a service provider. Its core question is this user from a trusted organization, and what are their attributes and permissions? It's the dominant protocol for federated identity in enterprise environments. SAML is built on a different technological stack using XML-based messages called SAML assertions, which are often digitally signed and exchanged via complex browser post redirects rather than direct API calls. SAML is the workhorse of corporate SSO, used to allow employees to log in once to their company's identity system and gain access to multiple internal and third-party enterprise applications without needing to re-authenticate. The relationship between OAuth 2.0 and OIDC is a powerful example of protocol layering. OAuth 2.0 provides the robust, flexible machinery for authorization and token issuance. OIDC then layers a standardized identity payload on top of that machinery. Before OIDC, developers were already using OAuth 2.0 for login, but they did so in proprietary ways. OIDC formalized and standardized this common practice, solving a clear market need without reinventing the underlying authorization framework. Understanding these distinctions is crucial for choosing the right protocol for your use case and for avoiding common implementation pitfalls. Now, let's look at some best practices for implementing OAuth 2.0 securely. After more than a decade of widespread implementation, the industry has developed a clear consensus on the most secure and effective ways to use the OAuth 2.0 framework. These best practices are essential for modern applications. First and foremost, use the right flow. Always use the authorization code grant with PKCE for all public clients, including SPAs and mobile apps. This is the most critical best practice and the foundation of secure OAuth 2.0 implementation. Second, actively deprecate and migrate away from insecure flows. The implicit grant and the resource owner password credentials grant should not be used in new applications. If you have existing applications using these flows, prioritize migrating them to more secure alternatives. Third, always use the state parameter in all redirect-based flows. This simple parameter correlates the authorization request with the response and mitigates cross-site request forgery attacks. It's a small detail that provides significant security benefits. Fourth, secure your redirect URIs. Use strict, exact string matching for redirect URI validation on the authorization server. Clients should register the most specific non-wildcard URI possible. This prevents attackers from intercepting authorization codes or tokens by manipulating redirect URIs. Fifth, practice good token hygiene. Use short-lived access tokens and long-lived, securely stored refresh tokens. Implement refresh token rotation, where a new refresh token is issued upon use to detect and invalidate compromised tokens. This limits the window of opportunity for token abuse. Sixth, enforce the principle of least privilege. Always request the narrowest possible scope required for your application's functionality. Don't ask for permissions you don't immediately need. This minimizes the potential impact of a compromised token. Finally, handle tokens securely. Never transmit tokens in URL query parameters. Always use the authorization bearer token header. Store tokens in the most secure location available for your client type, HTTP-only cookies for web apps, and platform keychain for mobile apps to protect them from cross-site scripting attacks. These best practices represent the collective wisdom of the security community and are essential for implementing OAuth 2.0 securely. By following them, you can leverage the benefits of OAuth 2.0 while avoiding common pitfalls that could compromise your application's security. But the OAuth 2.0 story doesn't end here. Let's look at what's coming next. The OAuth 2.0 framework continues to evolve. After more than a decade of implementation experience, the industry has developed a clear consensus on best practices, which is culminating in a new consolidated specification, OAuth 2.1. OAuth 2.1 is not a revolutionary new version of the protocol. Primary goal is to make it easier for developers to build secure applications by making the most secure patterns the default and removing outdated, insecure options. The key changes proposed in this draft include making PKCE mandatory for all clients, including confidential ones. This provides a consistent, high level of security for the most common flow. The specification formally deprecates and removes the insecure implicit grant, addressing a common source of vulnerabilities. It explicitly states the requirement for exact string matching of redirect URIs, eliminating ambiguity that has led to security issues. It simplifies the use of bearer tokens by removing other, less common token types, and clarifies the handling of refresh tokens, recommending that they be sender-constrained
or rotated upon use. The development of OAuth 2.1 represents a maturation of the framework. It signals a clear move toward a secure by default posture, aiming to guide developers away from common pitfalls and into what's sometimes called a pit of success. By pruning the evolutionary tree of grant types and codifying the lessons learned from years of real-world deployment, OAuth 2.1 promises to make the next generation of applications built on delegated authorization more secure, robust, and easier to implement correctly. Beyond OAuth 2.1, we're seeing exploration of new authorization models that address emerging use cases. These include more fine-grained authorization systems, better support for decentralized identity, and improved mechanisms for handling consent and data minimization. The future of authorization is likely to build on the foundation established by OAuth 2.0 while addressing new challenges in our increasingly interconnected digital landscape. What might this future look like? Imagine a world where authorization decisions are more dynamic, context-aware, and fine-grained, where users have even greater control over their data, and where interoperability between different identity systems is seamless. That's the direction we're heading, and OAuth 2.0 is laying the groundwork for that future. Now, let's wrap up with some key takeaways and next steps.
As we wrap up our comprehensive guide to OAuth 2.0, let's recap the key takeaways and consider next steps for further learning. First, OAuth 2.0 is fundamentally an authorization framework, not an authentication protocol. It enables delegated access, allowing one application to access resources in another on behalf of a user without sharing credentials. This distinction is crucial for understanding how OAuth 2.0 fits into the broader identity and access management landscape. Second, the security of OAuth 2.0 relies on several key principles: the separation of front-channel and back-channel communications, the use of short-lived access tokens with optional refresh tokens, and the implementation of the principle of least privilege through scopes. Third, choosing the right grant type for your application type is critical. The authorization code grant with PKCE is the recommended approach for most modern applications, while the client credentials grant is appropriate for machine-to-machine scenarios. Fourth, OAuth 2.0 doesn't exist in isolation. It's part of a broader ecosystem that includes OpenID Connect for authentication and SAML for enterprise federation. Understanding how these protocols relate to each other is essential for designing comprehensive identity and access management solutions. Finally, implementing OAuth 2.0 securely requires attention to best practices, from proper token management to secure redirect URI validation. The industry's collective experience has been codified in emerging standards like OAuth 2.1, which aim to make secure implementation the default path. If you're interested in diving deeper into OAuth 2.0, I recommend reading the RFC 6749 specification, exploring the implementation guides provided by major identity providers, and experimenting with building your own OAuth 2.0 client and server applications. There are also excellent open-source libraries and tools available for most programming platforms that can help you implement OAuth 2.0 correctly and securely. Remember, security is an ongoing journey, not a destination. As the digital landscape continues to evolve, so too will the protocols and best practices for securing it. By understanding the fundamentals of OAuth 2.0, you're well-equipped to navigate this evolving landscape and build secure, user-friendly applications. Thank you for joining me on this journey through OAuth 2.0. I hope you found this guide informative and that it empowers you to implement OAuth 2.0 securely and effectively in your own projects. Keep learning, stay curious, and build amazing things.